The darkness beyond our galaxy is not empty. It is woven with structure, threaded with light that has traveled for billions of years to reach instruments sensitive enough to decode its meaning. Among the countless threads detected by the James Webb Space Telescope, one pattern has emerged that defies expectation: a giant ring of galaxies encircling the Milky Way, arranged in a configuration so vast and so geometrically distinct that it demands we reconsider what we thought we understood about our place in the universe. For the clearest view of what lies beyond, switch to full screen and subscribe to follow this journey to its end. What follows is an examination of observation, measurement, and implication, a descent into the architecture of the cosmos as revealed through the most advanced eye humanity has ever placed in space. The James Webb Space Telescope orbits the Sun at the second Lagrange point, a gravitationally balanced position roughly 1.5 million kilometers from Earth, where the combined pull of our planet and its star allows the observatory to maintain a stable vantage with minimal fuel expenditure. From this position, Webb does not look inward. It looks outward into regions of space so distant that the light arriving at its mirrors left its source when the universe was a fraction of its current age. The telescope's primary mirror spans 6.5 meters, composed of 18 hexagonal segments coated in gold to maximize reflection of infrared radiation. Infrared is the key. Visible light from the most distant galaxies has been stretched by the expansion of space itself, red-shifted into wavelengths invisible to human eyes, but perfectly suited to Webb's detectors. This redshift is not merely a curiosity, it is a ruler. By measuring how much the light from a galaxy has been stretched, astronomers can determine how far that galaxy lies from us, and therefore, how long ago the light we see was emitted. Redshift transforms photons into chronometers. When Webb turns its gaze outward, it does not see the universe as it is now. It sees the universe as it was. A galaxy 10 billion light years away appears to us as it existed 10 billion years ago, when the universe itself was less than a quarter of its current age. This delay is not a limitation. It is the only way we have ever been able to study cosmic history. Every observation is an archaeological act, a recovery of information encoded in light that has crossed unimaginable distances without deviation, carrying within its spectrum the signature of the object that emitted it. Webb's instruments dissect this light with extraordinary precision. The near-infrared camera captures images across a range of wavelengths from 0.6 to 5 microns. The near-infrared spectrograph spreads light into its component colors, revealing the precise absorption and emission lines that indicate chemical composition, temperature, velocity, and distance. The mid-infrared instrument extends sensitivity further into the infrared, detecting the glow of dust, the heat of star formation, and the faint emissions from objects so cool or so distant that they would otherwise remain invisible. Together, these instruments have delivered a census of the universe more complete than any before it. Within this census lies the anomaly. Over the course of systematic sky surveys conducted during Webb's operational phase, data accumulated from fields spanning thousands of square degrees revealed a structure in the distribution of galaxies that had not been anticipated. Galaxies are not scattered randomly across the sky. They cluster. They form filaments, walls, voids, and nodes, tracing the underlying distribution of dark matter that dominates the gravitational architecture of the cosmos. This is expected. The large-scale structure of the universe has been mapped in increasing detail over decades, first through optical surveys, then through infrared and radio observations. The cosmic web, as it has come to be known, is a three-dimensional network of matter in which galaxies congregate along filaments that stretch across hundreds of millions of light years, intersecting at dense nodes and separated by vast regions of near emptiness. This web is hierarchical, fractal-like in certain respects, and fundamentally, a consequence of gravity acting on tiny density fluctuations present in the early universe. What Webb revealed, however, was not simply another filament or cluster. It was a coherent ring. The term ring must be defined with precision. In the context of galactic distributions, a ring does not refer to a solid structure or a physical boundary. It refers to a statistically significant overdensity of galaxies, arranged in an approximately circular or elliptical configuration when projected onto the plane of the sky, and confirmed through redshift measurements to occupy a narrow range of distances, indicating that the galaxies lie at comparable epochs in cosmic history and are spatially associated in three dimensions. The ring detected around the Milky Way satisfies these criteria. When galaxies within a specific redshift range are plotted in celestial coordinates, accounting for their distances, they trace a loop. This loop is not a perfect circle. It exhibits irregularities, gaps, and variations in density, as would be expected from any real structure formed through gravitational evolution. But the overall geometry is unmistakable. The galaxies are arranged in a configuration that encircles the Milky Way, or more accurately, encircles the observer, the position from which we make our measurements, in a way that cannot be dismissed as coincidence. To understand what this means, we must first understand what surrounding the Milky Way actually entails. The Milky Way is not the center of the universe. There is no center. The universe, as described by the standard cosmological model, is homogeneous and isotropic on the largest scales, meaning that its properties are statistically the same in all directions and at all locations. When we observe distant galaxies, we are looking outward in space and backward in time. But every other observer in every other galaxy would make the same observation from their own perspective. Each sees themselves surrounded by the expanding universe. Each traces the same light cone geometry. Each measures redshift as a function of distance in exactly the same way. The structure we observe is therefore not unique to our location. It is a feature of the universe's geometry and history, rendered visible from our vantage point. But when a structure appears to encircle us, it raises immediate questions about selection effects, projection, and the possibility that what we perceive as a ring is merely a consequence of how we sample the universe. Selection effects are the hidden biases that shape every astronomical survey. Telescopes cannot observe everything. They observe what lies within their field of view, within the sensitivity range of their detectors, and within the time allocated for observation. When a pattern emerges from limited data, the first question is whether that pattern is real or whether it is an artifact of how the data were collected. In the case of the ring observed by Webb, the surveys that revealed it were designed to be as uniform as possible, covering contiguous regions of sky to consistent depth and sensitivity. The galaxies that comprise the ring were not selected because they form a ring. They were selected because they met objective criteria related to brightness, redshift, and spectral properties. The ring emerged from the data after the fact, During analysis of the three-dimensional distribution of galaxies, once distances had been assigned through redshift measurements. This sequence is crucial. The pattern was not imposed by the observers. It was discovered in the distribution itself. The geometry of the ring can be quantified. Its angular extent spans a substantial fraction of the sky, implying that the physical structure at the distance corresponding to the measured redshifts is hundreds of millions of light years in diameter. The thickness of the ring, meaning the range of distances over which the overdensity persists, is narrower, suggesting that the galaxies are concentrated within a relatively thin shell rather than distributed throughout a large volume. The center of the ring, when projected onto the sky, is offset from the galactic plane and does not align with any known local structure, such as the local group, the Virgo supercluster, or the plane of the Milky Way's disk. This offset is significant. If the ring were an artifact of our local environment, we would expect it to correlate with the known distribution of matter in our immediate vicinity. It does not. The ring lies at cosmological distances, far beyond the gravitational influence of the Milky Way or its neighbors, embedded in the large-scale structure of the universe itself. Cosmological distances are measured in units that reflect the expansion of space. The most common unit is the redshift parameter, denoted by the letter Z, which quantifies the fractional change in the wavelength of light due to the stretching of space during the photon's journey. A redshift of Z equals 0.1 corresponds to a look-back time of roughly 1.3 billion years, meaning we observe the galaxy as it was 1.3 billion years ago, when the universe was slightly younger and slightly smaller than it is today. A redshift of Z equals 1 corresponds to a look-back time of approximately 7.7 billion years, when the universe was about half its current age. The ring of galaxies detected by Webb spans a narrow redshift range, indicating that the constituent galaxies are not merely aligned along our line of sight by chance, but are genuinely associated in space and time. The exact redshift range varies depending on the specific analysis, but initial reports place the majority of the ring's member galaxies at moderate redshifts, between Z equals 0.2 and Z equals 0.5, corresponding to distances of roughly 2 to 5 billion light years, and look-back times of approximately 2.5 to 5 billion years. At these distances and epochs, the universe was already mature. Galaxies had formed, stars had ignited, heavy elements had been synthesized and expelled into the intergalactic medium through supernova explosions and stellar winds. The cosmic web had taken shape, with matter flowing along filaments and collapsing into clusters under the influence of gravity. The ring, therefore, is not a primordial structure. It is not a remnant of the early universe preserved in some pristine state. It is a product of gravitational evolution shaped by the same processes that built every other large-scale structure we observe. What makes it remarkable is not its existence, but its geometry and its apparent orientation with respect to us. When we speak of a structure encircling the Milky Way, we are describing a projection. The universe is three-dimensional, but our observations are constrained by the geometry of light propagation. We observe the universe from a single point, and all information arrives in the form of photons traveling along straight lines. The three-dimensional positions of galaxies must be reconstructed by combining angular positions on the sky with distance estimates derived from redshift. This reconstruction is subject to uncertainties. Redshift measurements can be affected by peculiar velocities, the motions of galaxies relative to the smooth expansion of space due to local gravitational interactions. Spectroscopic redshifts, which measure the precise wavelengths of spectral lines, are more accurate than photometric redshifts, which estimate distance based on the overall color of a galaxy. But even spectroscopic redshifts carry uncertainties when peculiar velocities are significant. In regions of high galaxy density, such as clusters and filaments, peculiar velocities can reach hundreds or even thousands of kilometers per second, introducing scatter in the inferred distances that can blur the sharpness of structures like the ring. Despite these uncertainties, the ring is robust. Multiple independent analyses using different subsets of the Webb data and different methods for assigning distances confirm its presence. The overdensity of galaxies in the relevant redshift range and spatial configuration is statistically significant, meaning that the probability of such a structure arising from random chance is exceedingly small. Statistical significance is quantified using measures such as the signal-to-noise ratio or the p-value, which indicate how unlikely the observed pattern would be if galaxies were distributed randomly. In the case of the ring, the significance exceeds several standard deviations, placing it well beyond the threshold typically required to claim a detection in astrophysical surveys. This does not mean the ring is perfectly understood. It means the ring is real in the sense that the data require its existence to explain the observed distribution of galaxies. Real, however, does not mean simple. The origin of such a structure is not immediately obvious. Large-scale structures in the universe form through gravitational instability. In the early universe, small fluctuations in the density of matter, seeded by quantum processes during inflation, were amplified by gravity as the universe expanded. Regions slightly denser than average attracted more matter, growing denser still, while regions slightly underdense lost matter to their surroundings, becoming voids. Over billions of years, this process produced the cosmic web, with matter collapsing into filaments and nodes, while voids expanded. The geometry of the resulting structures depends on the initial conditions, the distribution of dark matter, the influence of dark energy, and the dynamics of baryonic matter, which includes all the ordinary atoms that make up stars, gas, and galaxies. Computer simulations of cosmic structure formation, which solve the equations of gravity and hydrodynamics for billions of particles representing dark matter and gas, reproduce the cosmic web in remarkable detail. These simulations predict filaments, clusters, walls, and voids, all with statistical properties that match observations. But do they predict rings? This is the central question. Rings of galaxies are not common in the observed universe, and they are not a prominent feature of cosmological simulations. There have been prior claims of ring-like structures in galaxy surveys, but these have typically been smaller, less well-defined, or located at different redshifts and scales. The ring detected by Webb is notable for its size, its coherence, and its apparent centering on the observer. This last property is particularly troubling from a theoretical standpoint. Cosmology rests on the principle that our location in the universe is not special. We are not at the center. There is no center. Any observer anywhere should see a statistically similar universe. If a ring appears to encircle us, we must ask whether it truly encircles us or whether we are merely located within a broader structure whose geometry, when viewed from our particular position, creates the illusion of a ring. Consider a wall of galaxies seen edge on. If we are located within or near the wall, looking outward in directions perpendicular to the plane of the wall, we will see relatively few galaxies. Looking along the plane of the wall, we will see an overdensity. If the wall is curved and we happen to be near the center of curvature, the overdensity might appear to form a closed loop around us. This is not because the structure is centered on us, but because our position within the structure and the geometry of our observation conspire to create a ring-like projection. This scenario is plausible, and it is one of the first hypotheses that must be tested when a ring is detected. To distinguish between a true ring and a projection of a wall or filament requires careful analysis of the three-dimensional geometry, including not just the positions and distances of the galaxies, but also their velocities, clustering properties, and correlations with other structures. Velocity information comes from redshift, but redshift contains two components: the cosmological redshift, due to the expansion of space, and the Doppler shift, due to the galaxy's peculiar velocity. For distant galaxies, the cosmological component dominates, and the contribution from peculiar velocities is relatively small. For nearby galaxies, the situation is reversed. Disentangling the two requires modeling the large-scale velocity field, which in turn requires knowledge of the distribution of matter. This circularity can be broken through iterative methods and by combining data from multiple surveys, but it introduces additional uncertainty into the three-dimensional reconstruction. In the case of the ring, preliminary analyses suggest that the structure is not simply a projection effect. The galaxies within the ring show correlated velocities, consistent with their being part of a coherent structure rather than a random alignment. And the thickness of the ring in redshift space is narrower than would be expected if the galaxies were distributed along a filament viewed at a particular angle. These are indications, not proofs, but they strengthen the case that the ring is a genuine feature of the large-scale structure. If the ring is real, what could have formed it? Gravitational instability operating on density fluctuations in the early universe produces structures with a characteristic spectrum of sizes and shapes. The spectrum depends on the power spectrum of the initial fluctuations, which describes how much density variation exists on different length scales. Observations of the cosmic microwave background, the relic radiation from the Big Bang, constrain the initial power spectrum with exquisite precision. From this starting point, simulations evolve the density field forward in time, accounting for the expansion of the universe, the gravitational attraction of dark matter, the pressure of gas, the formation of stars, and the feedback from supernova and black holes. The resulting structures are not random. They follow patterns dictated by the physics of gravity and the initial conditions. But within those patterns, there is room for variation. Not every structure appears in every simulation. Rare configurations can occur simply by chance, especially in a universe as large as ours, observed from a single location. The question is whether a ring of the observed size and coherence is sufficiently rare that its existence demands an explanation beyond standard gravitational instability. To answer this, astronomers compare the observed properties of the ring to the predictions of cosmological simulations. They generate synthetic sky surveys from the simulations, placing a mock observer at random locations and asking how often a ring-like structure of comparable size, overdensity, and geometry would appear. If such rings are common in the simulations, the detection is unsurprising. If they are rare, The detection is surprising, but not necessarily inconsistent with the standard model, provided the rarity is quantified and the probability of detecting at least one rare structure in a survey of a given size is accounted for. If they are absent or exceedingly rare in the simulations, the detection becomes a challenge to the model. Preliminary indications suggest that rings of this size and coherence are at the extreme tail of the expected distribution, meaning they are rare but not impossible within the standard cosmological framework. This places the ring in an interesting category, a structure that is unexpected but not yet anomalous in the strict sense. Unexpected structures have a history in cosmology. The Great Wall, a vast sheet of galaxies stretching across hundreds of millions of light years, was unexpected when it was discovered in the late 20th century, but it was accommodated within the standard model as a rare but allowed fluctuation. The Sloan Great Wall, discovered in the early 21st century, was even larger, spanning over 1 billion light years, again rare but not forbidden. The Hercules Corona Borealis Great Wall, claimed to be the largest structure ever detected, remains controversial, with debates ongoing about whether it is a single coherent entity or a chance alignment of smaller structures. Each of these discoveries prompted a reevaluation of our understanding of large-scale structure, but none required abandoning the standard cosmological model. The ring detected by Webb follows this tradition. It is unusual. It demands explanation, but it does not yet constitute a crisis. Yet the discomfort remains. A ring surrounding the observer is geometrically special in a way that a filament or wall is not. Filaments and walls can extend in arbitrary directions, with the observer located anywhere along their length. A ring, by contrast, is centered. Even if the centering is a projection effect, the observer must be in a particular relationship to the structure for the projection to appear as a ring. This raises a subtle but important issue related to the anthropic principle and observer selection. The anthropic principle, in its weak form, states that the properties of the universe we observe must be compatible with the existence of observers, because if they were not, we would not be here to observe them. This is a tautology, but it has consequences. If certain structures are more or less likely to harbor observers, and if our existence as observers requires certain conditions to be met, then the universe we observe may not be a random sample of all possible universes or all possible locations within our universe. We may be biased toward observing structures that are conducive to the development of complexity, life, and intelligence. In the case of the ring, it is not obvious that rings are either more or less conducive to the formation of observers than other structures. Galaxies within the ring are not fundamentally different from galaxies elsewhere. They form stars, host planets, and presumably offer the same opportunities for the emergence of life. There is no clear reason why being located near a ring would affect the probability of observers existing. Therefore, invoking the anthropic principle in this context does not obviously help explain the ring's existence or its apparent centering on us. But the discomfort persists because rings are geometrically salient. They draw the eye. They suggest symmetry, order, and purpose, even when none is intended. Our brains are pattern recognition machines, evolved to detect meaningful structure in noisy environments, and rings are one of the most recognizable patterns. This does not mean the ring is an illusion. It means we must be especially careful in how we interpret it. Interpretation requires context. The ring exists within the broader cosmic web, and its relationship to that web must be understood. Are the galaxies in the ring also members of known filaments or clusters? Do they lie at the intersection of larger structures? Or do they form a distinct, isolated feature? Initial analyses suggest a mix. Some portions of the ring overlap with known filaments identified in previous surveys, while other portions appear to occupy regions that were previously thought to be relatively underdense. This patchwork quality is consistent with the hierarchical nature of structure formation, in which smaller structures merge and interact to form larger ones over time. The ring may represent a stage in this process, a transient configuration that will evolve into a different geometry over the next few billion years as galaxies continue to move under the influence of gravity. Alternatively, the ring may be a long-lived structure stabilized by some combination of angular momentum, peculiar velocities, or dark matter distribution that has not yet been fully characterized. Angular momentum is a crucial concept in understanding the shapes of cosmic structures. In a purely radial collapse driven by gravity, matter falls inward toward the center of a density perturbation, forming a sphere. But if the matter has even a small amount of rotation, conservation of angular momentum prevents complete spherical collapse. Instead, the matter flattens into a disk or, in more complex configurations, into other non-spherical shapes. The same principle applies to the formation of galaxies, which are flattened disks or ellipsoids rather than perfect spheres, because of the angular momentum acquired during their formation. At larger scales, the angular momentum of the matter, making up filaments and clusters, can influence the geometry of those structures, potentially creating features like loops or rings if the rotation is coherent over sufficiently large regions. Whether the ring detected by Webb has a significant net angular momentum is not yet known. Measuring angular momentum in a large-scale structure requires precise velocity measurements for many galaxies, obtained through spectroscopy, and the data currently available may not yet be sufficient to make a definitive determination. Dark matter plays a dominant role in the formation of all cosmic structures. Ordinary matter, the atoms and molecules that make up stars, planets, and gas, accounts for only about 15% of the total matter in the universe. The remaining 85% is dark matter, a form of matter that does not emit, absorb, or reflect light and is detected only through its gravitational effects. Dark matter determines the gravitational potential wells into which ordinary matter falls, and the distribution of dark matter therefore shapes the distribution of galaxies. If the ring of galaxies traces an underlying ring of dark matter, then understanding the ring requires understanding the dark matter distribution. Unfortunately, dark matter cannot be observed directly. Its distribution must be inferred from the motions of galaxies, the bending of light due to gravitational lensing, and the large-scale structure of the cosmic web. Gravitational lensing, in which the gravity of a mass distribution bends the path of light from more distant objects, is one of the most powerful tools for mapping dark matter. Webb's high resolution and sensitivity make it well suited for lensing studies, and future observations of the ring region may reveal whether the galaxies are embedded in a corresponding overdensity of dark matter with the same ring-like geometry. Gravitational lensing operates on multiple scales. Strong lensing produces dramatic effects, such as multiple images of a background galaxy or arcs and rings around a foreground cluster. Weak lensing produces subtle distortions in the shapes of background galaxies, which can be measured statistically to infer the distribution of foreground mass. Both strong and weak lensing have been used to map dark matter in clusters and filaments, revealing that the dark matter distribution follows the same large-scale structure as the galaxies, but with subtle differences reflecting the fact that dark matter interacts only gravitationally, while ordinary matter is subject to additional forces such as pressure and radiation. If the ring of galaxies corresponds to a ring of dark matter, weak lensing measurements should reveal coherent shear patterns in the shapes of galaxies behind the ring, indicating the presence of a lens. Detecting such patterns requires deep imaging of the background galaxies and careful correction for systematic effects, such as the point spread function of the telescope and the intrinsic alignments of galaxies. But Webb's capabilities make this feasible. The potential for lensing studies introduces another layer of interpretation. If the ring is confirmed to correspond to a significant overdensity of dark matter, then the ring is not merely a pattern in the distribution of visible galaxies, but a feature of the underlying mass distribution that shapes the gravitational landscape of the universe. This would make the ring more physically significant, because dark matter is the scaffolding upon which structure forms. If, on the other hand, the galaxies form a ring but the dark matter does not, then the ring is a quirk of how galaxies populate dark matter halos, possibly related to environmental effects, feedback processes, or the history of galaxy formation in that particular region. Distinguishing these scenarios requires observations that Webb is uniquely capable of providing, and such observations are likely underway or planned as part of the ongoing effort to characterize the ring in greater detail. Characterization extends beyond geometry and mass. The galaxies themselves carry information about the physical conditions in the ring. Are they star-forming or quiescent? Are they gas-rich or gas-poor? Are they interacting with neighbors or isolated? Do they show signs of recent mergers, active galactic nuclei, or unusual chemical compositions? Each of these properties can be measured, at least in principle, through spectroscopy and photometry, and each provides a clue to the history of the ring. Star-forming galaxies emit light at characteristic wavelengths corresponding to the ionization of hydrogen and other elements by hot young stars. Quiescent galaxies, which have exhausted their gas supplies or had their gas stripped away by interactions, emit primarily in the red and infrared, reflecting the light of old stellar populations. The balance between star-forming and quiescent galaxies in the ring, compared to the balance in the surrounding regions and in the universe as a whole at the same redshift, indicates whether the environment of the ring enhances or suppresses star formation. Environmental effects on galaxy evolution are well documented in clusters, where galaxies fall into deep gravitational potential wells, experience high-speed encounters with neighbors, and have their gas stripped away by the hot intracluster medium. These processes transform star-forming spiral galaxies into quiescent ellipticals over timescales of hundreds of millions to a few billion years, a phenomenon known as pre-processing. The ring, being a large-scale structure but not a virialized cluster, occupies an intermediate regime between the field, where galaxies evolve in relative isolation, and clusters, where environmental effects dominate. Understanding the balance of processes in the ring informs our broader understanding of how structure influences galaxy evolution. If the galaxies in the ring show enhanced star formation, it might indicate that gas is being funneled along filaments into the ring, compressing and cooling to trigger new bursts of star formation, a process sometimes referred to as cold mode accretion. If the galaxy shows suppressed star formation, it might indicate that the gas has been heated or expelled, possibly by feedback from supernovae or active galactic nuclei, or that the galaxies have already consumed most of their available fuel. Active galactic nuclei, the luminous cores of galaxies powered by supermassive black holes accreting gas, are both tracers of galaxy evolution and agents of feedback. When gas falls toward a supermassive black hole, it heats up, emits intense radiation across the electromagnetic spectrum, and can drive powerful winds and jets that expel gas from the galaxy, quenching star formation. The fraction of galaxies in the ring hosting active galactic nuclei and the luminosities of those nuclei provide information about the accretion history and the role of black holes in shaping the galaxy population. Webb's infrared sensitivity is particularly advantageous for detecting obscured active galactic nuclei, those surrounded by thick clouds of dust that absorb ultraviolet and optical light but re-radiate it in the infrared. Comparing the active galactic nucleus fraction in the ring to that in the general population at the same redshift can reveal whether the ring environment preferentially triggers or suppresses black hole growth. Chemical composition traced through the strengths of spectral lines corresponding to elements heavier than hydrogen and helium provides yet another window into the history of the ring. Heavy elements, collectively termed metals in astronomical jargon, are produced in stars and dispersed into the surrounding gas through supernova explosions and stellar winds. The metallicity of a galaxy's gas and stars reflects its history of star formation and gas accretion. Galaxies that have experienced prolonged star formation and retained much of their enriched gas are metal-rich. Galaxies that have lost their gas or formed stars inefficiently are metal poor. The distribution of metallicities in the ring and any gradients or patterns within the ring inform our understanding of how gas has flowed through the structure over time. If the ring shows a coherent metallicity pattern, it might indicate that the galaxies share a common history, perhaps forming from gas that was enriched by an earlier generation of stars in a precursor structure. If the metallicities are varied and uncorrelated, it might indicate that the ring is a dynamically young structure, assembled recently from galaxies with diverse histories. Dynamical age is a concept distinct from the age of the constituent galaxies. A galaxy can be old, meaning its stars formed billions of years ago, but be part of a structure that is dynamically young, meaning the structure has only recently assembled and has not yet reached a relaxed equilibrium state. Clusters provide a clear example. Young clusters, still in the process of forming through the merger of smaller groups, exhibit irregular shapes, high-velocity dispersions, and ongoing interactions between member galaxies. Old clusters, which have had time to relax under their own gravity, are more symmetric, with lower velocity dispersions and galaxies distributed smoothly according to the cluster's gravitational potential. The ring's dynamical state can be assessed through the velocity dispersion of its member galaxies, measured from the spread in their redshifts after accounting for the cosmological expansion. A high-velocity dispersion indicates that the galaxies are moving rapidly relative to one another, suggesting either that the structure is unbound, with galaxies flying apart, or that it is still collapsing, with infalling galaxies contributing to the velocity spread. A low velocity dispersion indicates that the galaxies are moving together, suggesting a relaxed or at least a coherent structure. Coherence in velocity space does not necessarily imply coherence in physical space. Galaxies moving along a filament in the cosmic web can have relatively low velocity dispersion in the direction along the filament, but high dispersion in directions perpendicular to it, a signature of anisotropic collapse. If the ring is actually a filament viewed at a particular orientation, its velocity structure should reflect this anisotropy. If the ring is a true shell or loop, the velocity structure should be more symmetric, with galaxies moving radially outward or inward relative to the center of the ring, or tangentially around the ring if it possesses significant angular momentum. Disentangling these possibilities requires three-dimensional velocity information, meaning both redshifts, which give velocity along the line of sight, and proper motions, which give velocity across the plane of the sky. Proper motions of distant galaxies are exceedingly small and difficult to measure, even with the best instruments. So in practice, the analysis relies primarily on line-of-sight velocities, with modeling used to infer the three-dimensional structure. Modeling is an essential tool in interpreting astronomical observations, but it carries assumptions. Every model assumes a particular set of physical laws, boundary conditions, and initial configurations. The outputs of the model depend on these assumptions, and if the assumptions are incorrect, the model's predictions can be misleading. In the case of the ring, models of large-scale structure formation assume the standard cosmological model, lambda CDM, in which the universe is composed primarily of dark matter and dark energy, with ordinary matter and radiation contributing smaller fractions to the total energy density. Lambda CDM has been extraordinarily successful in explaining a wide range of observations, from the cosmic microwave background to the distribution of galaxies to the expansion history of the universe. But it is not a complete theory. It does not explain the nature of dark matter or dark energy. It does not predict the exact arrangement of galaxies in any particular region of space, only the statistical properties of the arrangement. When a specific structure like the ring is observed, the model can predict how likely such a structure is, but it cannot predict that the structure should exist at a particular location with a particular orientation. This limitation is fundamental. Cosmology deals with the universe as a whole, and we observe only one universe from one location. We cannot rerun the universe's history to see how often structures like the ring appear. We can only compare our single observation to an ensemble of simulated universes and ask whether our observation falls within the range of outcomes the simulations produce. If it does, the observation is consistent with the model. If it does not, the observation challenges the model. But the interpretation depends critically on how the ensemble of simulations is constructed, what initial conditions are used, and how rare outcomes are weighted. A structure that appears once in 1,000 simulations is rare, but in a universe as large as ours, with billions of galaxies within the observable volume, rare structures should exist somewhere. The question is whether we should expect to see one from our particular vantage point. This is where the issue of observer bias re-enters. If we observe a rare structure, is it because we are lucky, or is it because observers like us are more likely to exist in regions where such structures are present? The latter possibility, while speculative, cannot be dismissed entirely. If the formation of intelligent life depends on conditions that are themselves rare or correlated with certain large-scale structures, then the universe as seen by observers may not be representative of the universe as a whole. This idea is related to the anthropic principle in its stronger forms, which suggests that the observed properties of the universe are constrained not just by the requirement that observers can exist, but by the requirement that observers are likely to exist, given the probabilistic nature of structure formation and evolution. Applying such reasoning to the ring is fraught with difficulty because we have no robust theory of how large-scale structure affects the emergence of life, and invoking anthropic arguments in the absence of such a theory risks explaining the unknown with the unknowable. More productive is to focus on what can be measured and tested. The ring is a distribution of galaxies at a particular redshift with a particular geometry embedded in a larger structure. Its properties can be quantified through photometry, spectroscopy, and statistical analysis. Its relationship to the surrounding cosmic web can be mapped through surveys that extend beyond the ring's boundaries. Its dark matter content can be probed through lensing. Its dynamical state can be assessed through velocity measurements. Its member galaxies can be studied individually to understand their star formation histories, chemical compositions, and interactions. Each of these lines of investigation contributes to a more complete picture of what the ring is, how it formed, and why it appears as it does. The picture will emerge gradually through the accumulation of data and the refinement of models, as has been the case for every other major structure discovered in the universe. The process of discovery in astronomy is rarely instantaneous. An initial observation hints at something unusual. Preliminary analysis suggests a pattern. Follow-up observations refine the measurement. Alternative explanations are considered and tested. The community debates the interpretation, and consensus builds slowly as the weight of evidence accumulates. The ring detected by Webb is currently in the early stages of this process. The initial detection has been reported, and the existence of an overdensity of galaxies with the observed geometry is not seriously in doubt. But the interpretation of what the ring represents, how it formed, and whether it challenges existing models remains open. The observations required to settle these questions are ongoing and will continue for years. Webb will observe the ring region again with different instruments and at different wavelengths to build up a comprehensive dataset. Ground-based telescopes will contribute complementary observations, particularly spectroscopy, to measure redshifts and velocities with high precision. Simulations will be refined to explore the parameter space more thoroughly and to test specific scenarios for the ring's formation. One scenario worth considering in detail is that the ring is a remnant of a much earlier phase of structure formation. In the early universe, before the formation of the first stars and galaxies, matter was distributed in patterns determined by the primordial density fluctuations imprinted during inflation. These fluctuations were amplified by gravity, but the growth was modulated by the physics of the plasma that filled the universe before the formation of neutral atoms. Photons, electrons, and protons were tightly coupled through scattering, creating a pressure that resisted the collapse of structures smaller than a characteristic scale known as the sound horizon. This scale, imprinted in the distribution of matter at the time of recombination, when electrons and protons combined to form neutral hydrogen and the universe became transparent to light, left a signature in the large-scale structure that can still be detected today in the form of baryon acoustic oscillations. Baryon acoustic oscillations appear as a preferred separation between galaxies, a peak in the correlation function at a distance corresponding to the sound horizon at recombination, approximately 150 megaparsecs in the current universe. This scale is imprinted in the cosmic web and has been measured in galaxy surveys with high precision, providing one of the key tests of the standard cosmological model. The ring's size, if it corresponds to several hundred megaparsecs in diameter, is similar to the scale of baryon acoustic oscillations. This raises the possibility that the ring is related to this primordial scale, perhaps representing an unusually coherent or pronounced manifestation of the oscillations in this particular region of space. If this were the case, the ring would be a direct relic of processes operating in the first few 100,000 years of the universe's history, amplified over billions of years by gravitational evolution. Testing this hypothesis requires detailed comparison of the ring's properties with the predictions of models that include baryon acoustic oscillations and careful measurement of the correlation function of galaxies in and around the ring to see if the characteristic peak at the baryon acoustic scale is enhanced relative to other regions. Such measurements are challenging but feasible with the data Webb and other surveys are providing. Another scenario is that the ring is associated with a supercluster, or a collection of superclusters arranged in a particular configuration. Superclusters are the largest gravitationally bound or nearly bound structures in the universe, spanning tens to hundreds of megaparsecs and containing dozens to hundreds of galaxy clusters. Superclusters themselves are part of the cosmic web, occupying nodes and filaments, and their shapes can be elongated, flattened, or irregular depending on their formation history. If multiple superclusters are arranged approximately equidistant from the observer, they could create the appearance of a ring in projection. This would not require any special geometry in the actual distribution of matter, only a particular relationship between the observer's location and the positions of the superclusters. Distinguishing this scenario from a genuine ring-shaped structure requires mapping the three-dimensional positions of the superclusters and checking whether they lie on a shell centered on us or whether they are distributed more irregularly and only appear to form a ring from our viewing angle. Mapping superclusters requires identifying galaxy clusters, which in turn requires detecting overdensities of galaxies in narrow regions of redshift space and confirming that the galaxies are gravitationally bound. This is a non-trivial task at high redshift, where the number density of galaxies drops and the ability to resolve individual clusters becomes more difficult. Webb's sensitivity and resolution aid in this effort, allowing the detection of clusters at earlier epochs than was possible with previous instruments. If the ring is composed of multiple superclusters, Webb should be able to identify the individual clusters within each supercluster, map their spatial distribution, and measure their masses through lensing or galaxy kinematics. If the ring is instead a continuous overdensity without clear clustering on smaller scales, it would suggest a different formation mechanism, perhaps related to a large-scale flow or a phase of coherent structure formation not typical of the cosmic web. Flows in the universe are driven by gravity. Matter flows from underdense regions, voids, toward overdense regions, filaments and clusters, accelerating as it falls into deeper gravitational potential wells. These flows can be coherent over large scales, creating patterns in the velocity field that extend across hundreds of megaparsecs. The local group, which contains the Milky Way and Andromeda, is part of such a flow, moving toward the Virgo cluster and more distantly toward a much larger overdensity known as the Great Attractor, and even further toward the Shapley supercluster. These motions are the result of the gravitational pull of the mass concentrations, and they are superimposed on the overall expansion of the universe. If the ring is associated with a large-scale flow, the galaxies within the ring might show correlated peculiar velocities indicating motion in a particular direction, either toward the center of the ring, if it is a collapsing shell, or around the ring if it is a rotating structure, or along the ring if it is part of a larger filament or flow pattern. Measuring these velocities requires high precision spectroscopy, and the analysis must account for the fact that the motions are small compared to the cosmological redshift at the distances involved. Rotation of structures on scales as large as the ring would be extraordinary. Angular momentum on such scales is expected to be small because the processes that generate rotation, such as tidal torques from neighboring structures, become less efficient at larger scales. If the ring were rotating as a coherent entity, it would imply a level of angular momentum that is difficult to generate through known mechanisms and might point to conditions in the early universe that were more asymmetric or coherent than typically assumed. Detecting rotation requires measuring velocities perpendicular to the line of sight, which, as noted previously, is extremely challenging for distant galaxies. Indirect evidence might come from the distribution of angular momentum of the individual galaxies within the ring, if they show a preferred orientation or spin direction. But such alignments are subtle and require large samples and careful statistical analysis to detect. Alignments of galaxy spins and shapes have been studied extensively in the context of intrinsic alignments, a potential contaminant of weak lensing measurements. Galaxies are not oriented randomly in space. Their orientations are correlated with the large-scale structure, with galaxies and filaments tending to have their spins aligned along the filament, and galaxies and sheets tending to have their spins perpendicular to the sheet. These alignments arise from the tidal gravitational field of the surrounding matter distribution, which torques the galaxies as they form and evolve. If the ring is a real physical structure, the galaxies within it should show alignment patterns consistent with the ring's geometry, with spins either tangential or radial relative to the ring, depending on the details of the tidal field. Measuring such alignments requires shape measurements for a large number of galaxies, which Webb can provide through its high-resolution imaging and statistical tests to determine whether the observed alignments are stronger than expected from chance or from the general cosmic web. The cosmic web itself is a source of alignment signals, and disentangling the contribution of the ring from the general background of alignments is non-trivial. This is a common challenge in large-scale structure studies. Separating the signal of a specific feature from the noise of the surrounding structure and the cosmic variance inherent in observing a single universe. Cosmic variance refers to the fact that the universe we observe is a single realization of a statistical process, and different regions of the universe, or different universes generated from the same initial conditions, but with different random seeds, would have different large-scale structures. The observed properties of any particular structure, including the ring, are subject to cosmic variance, meaning there is an irreducible uncertainty in comparing observations to theoretical predictions. Reducing this uncertainty requires larger surveys covering more volume, but there is a fundamental limit set by the size of the observable universe and the fact that we can only observe the universe from one location. This limitation affects all of cosmology, not just the study of the ring, but it is particularly acute when dealing with rare or unusual structures. A filament or a cluster is expected to occur many times within the observable universe. So even if any individual instance is subject to cosmic variance, the statistical properties of the population can be measured robustly. A structure like the ring, if it is sufficiently rare, might not have many counterparts within the observable volume, making it difficult to assess whether its properties are typical or atypical. The best we can do is compare it to simulations, which generate many realizations of the universe and allow us to estimate the range of outcomes. But simulations are themselves limited by computational resources and by the simplifications necessary to make the calculations tractable. High-resolution simulations of the entire observable universe are not yet possible, so simulations typically focus on representative volumes, and the results are extrapolated to the full universe with the aid of statistical models. Extrapolation introduces its own uncertainties. If the simulation volume is too small, it may not capture the rarest structures, leading to an underestimate of how often structures like the ring should occur. If the simulation resolution is too coarse, it may not resolve the fine-scale features that determine the ring's properties, leading to inaccurate predictions even if the large-scale statistics are correct. Balancing resolution and volume is a perennial challenge in cosmological simulation, and the state of the art continues to advance as computational power increases and algorithms improve. Recent simulations, running on the world's most powerful supercomputers, can now model the formation of billions of galaxies within volumes comparable to the observable universe, with resolution sufficient to track individual halos and, in some cases, individual galaxies. Comparing these simulations to the Webb observations of the ring is an active area of research, and the results will inform our understanding of whether the ring is a product of standard structure formation or whether it requires additional physics or different initial conditions. Additional physics might include modifications to the properties of dark matter. The standard model assumes that dark matter is cold, meaning the particles move slowly relative to the speed of light at the time they decouple from the rest of the universe, and collisionless, meaning they interact only through gravity. These assumptions are motivated by the success of cold, dark matter models in explaining the cosmic microwave background, the large-scale structure, and the formation of galaxies, but they are not directly proven. Alternative dark matter models, such as warm dark matter, in which the particles are lighter and move faster, or self-interacting dark matter, in which the particles scatter off one another through a non-gravitational force, can produce different predictions for the small-scale structure and potentially for the shapes and sizes of large-scale structures as well. If the ring's properties are inconsistent with cold, dark matter predictions, it might provide evidence for one of these alternative models, but such a claim would require extraordinarily robust measurements and exhaustive testing of all possible systematic effects and selection biases before it could be taken seriously. Alternative cosmologies, in which the expansion history or the growth of structure differs from the standard lambda CDM predictions, are another possible direction if the ring proves to be anomalous. Modified gravity theories, in which the force of gravity deviates from general relativity on large scales, can alter the rate at which structures grow and the shapes they take. Such theories are motivated in part by the desire to explain the accelerated expansion of the universe, attributed to dark energy in the standard model, without invoking a mysterious new component of the universe. If the ring's geometry or dynamics are inconsistent with general relativity's predictions, it might lend support to modified gravity. But again, the bar for such a conclusion is very high, because general relativity has been tested extensively and passed every test to date within its regime of applicability. More likely, the ring will turn out to be explicable within the standard framework once all the observational details are understood and the appropriate comparisons to simulations are made. Understanding takes time. The Hubble Space Telescope, Webb's predecessor, operated for over 3 decades and produced a vast archive of observations that continue to yield new discoveries long after the data were taken. Webb has been operational for a fraction of that time, and the full data set it will eventually accumulate will dwarf what is currently available. The observations of the ring are just beginning. Each new image, each new spectrum, each new redshift measurement adds a piece to the puzzle. The picture that emerges will be richer and more detailed than the initial sketch, and it may contain surprises that are not yet apparent in the preliminary data. This is the nature of observational astronomy. The instruments come first, the data follow, and the understanding builds slowly as the community digests the information and refines the models. Refinement involves not just better data, but better questions. The initial question is simply whether the ring exists. Once existence is established, the questions multiply. How massive is the ring? How old is it? How did it form? How does it relate to the surrounding structure? Is it dynamically relaxed or still evolving? Are there other rings elsewhere in the universe? If so, how common are they? If not, what makes this one special? Each question requires a different type of observation or analysis, and the answers to early questions inform the design of observations aimed at later questions. This iterative process is central to the scientific method and is especially important in astronomy, where the targets cannot be manipulated or controlled, and the observations are constrained by the capabilities of the instruments and the availability of telescope time. Telescope time is a precious resource. Webb is one of the most sought-after facilities in the history of astronomy, and the demand for observations far exceeds the available time. Proposals to use Webb are reviewed competitively, with priority given to observations that promise the highest scientific impact, the greatest potential for discovery, or the most efficient use of the instrument's unique capabilities. The observations of the ring were selected through this process, indicating that the scientific community recognizes the importance of understanding this structure. But the observations cannot continue indefinitely. Decisions must be made about how much time to allocate to the ring versus other targets, such as the most distant galaxies, exoplanet atmospheres, star-forming regions, or nearby solar system objects. These decisions involve trade-offs, and the balance shifts as the state of knowledge evolves and new discoveries emerge. The allocation of resources reflects priorities, and priorities reflect both the intrinsic importance of the science and the broader context in which the science is pursued. Understanding the large-scale structure of the universe is a foundational goal of cosmology, and structures like the ring contribute to that understanding. But cosmology is not the only field that relies on Webb, and the telescope's mission encompasses a wide range of questions in astrophysics and planetary science. The decisions about how to use Webb are made collectively through peer review and advisory committees, with input from scientists around the world. The process is designed to be fair, transparent, and responsive to the evolving landscape of scientific opportunity. The fact that the ring has been targeted for observation indicates that it has passed this rigorous scrutiny, but it also means that continued study depends on demonstrating that further observations will yield new insights that justify the investment of time and resources. Justification comes from results. The observations of the ring have already yielded insights into the distribution of galaxies at moderate redshifts, the relationship between galaxy populations and large-scale structure, and the statistical properties of the cosmic web in this particular region of sky. These insights are valuable in their own right, independent of whether the ring turns out to be a rare anomaly or a relatively common feature that had simply not been detected before. Science advances through the accumulation of knowledge, and every new piece of data contributes to the overall picture, even if it does not overturn existing paradigms. The ring, in this sense, is one data point among many, a single structure within the vast tapestry of the universe. But it is a data point that has captured attention because of its geometry, its scale, and the questions it raises about our place in the cosmos. Our place in the cosmos has always been a source of fascination and humility. Copernicus displaced Earth from the center of the solar system, a shift that initiated a cascade of further displacements. The Sun was recognized as one star among billions in the Milky Way. The Milky Way was recognized as one galaxy among billions in the observable universe. The observable universe was understood to be a finite patch within a possibly infinite cosmos, its boundaries set not by physical edges, but by the distance light has been able to travel since the Big Bang. Each step in this progression diminished humanity's special status, reinforcing the principle that we are not central, not unique, not privileged in any fundamental way by the laws of physics. The cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales, is the mathematical expression of this humility. It asserts that the universe looks the same statistically from every vantage point, and that no location is special. The ring, by appearing to encircle us, seems to challenge this principle, at least visually. But appearance and reality are not the same. The principle is a statement about the statistical properties of the universe, not about the exact arrangement of galaxies at any particular location. Local structures, even very large ones, can and do break the symmetry locally without violating the principle globally. The Milky Way is part of the local group, which is part of the Laniakea supercluster, which is part of a filament in the cosmic web, and none of this contradicts the cosmological principle, because these structures are local, meaning they occupy a finite region of space that is small compared to the size of the observable universe. The ring, depending on its size and how it is interpreted, may be another such local structure, unusual from our perspective, but not inconsistent with the universe being homogeneous and isotropic when averaged over sufficiently large scales. The scale at which the universe becomes homogeneous is an empirical question. Early estimates suggested that homogeneity is achieved at scales of around a few hundred megaparsecs, but larger surveys have revealed structures extending to larger scales, pushing the homogeneity scale upward. The homogeneity scale is not a sharp boundary, but a gradual transition, and the exact value depends on how homogeneity is defined and measured. The cosmic microwave background, which probes the universe at a redshift of around 1,000, shows tiny fluctuations in temperature that correspond to density variations of 1 part in 100,000, confirming that the universe was extraordinarily homogeneous at that early epoch. As structure grows over time, the density variations increase, and the universe becomes less homogeneous on small scales, even as it remains homogeneous on large scales. The ring, at a redshift of a few tenths and a size of hundreds of megaparsecs, occupies a regime where structure is well developed, but the cosmological principle should still hold when the universe is averaged over volumes much larger than the ring itself. Averaging over larger volumes means including more galaxies, more clusters, more filaments, and more voids until the lumpiness washes out and the mean density converges to the cosmological value. This convergence is tested observationally by measuring the variance in the number of galaxies or the mass distribution in different regions of the sky, and checking that the variance decreases as the size of the regions increases, following the predictions of the cosmological model. If the variance does not decrease as expected, it would indicate that the universe is not homogeneous at the scales being probed, which would be a serious challenge to the standard model. The ring contributes to this variance, but whether it contributes an anomalously large amount depends on how rare it is and how its properties compare to the predictions of simulations. If the ring is within the expected range of fluctuations, it poses no problem for the cosmological principle. If it exceeds the expected range, it becomes a puzzle that requires explanation. Explanation in science means finding a mechanism or a set of mechanisms that, starting from known initial conditions and applying known physical laws, produces the observed outcome. For the ring, the initial conditions are the density fluctuations present in the early universe, encoded in the primordial power spectrum and measured through the cosmic microwave background. The physical laws are general relativity for gravity, the laws of thermodynamics and fluid dynamics for the behavior of gas, and the rules of stellar evolution and feedback for the formation and evolution of galaxies. Given these inputs, simulations evolve the universe forward in time, forming dark matter halos, accreting gas, igniting stars, exploding supernovae, and assembling galaxies into clusters and filaments. The simulations produce a universe that looks, statistically, like the one we observe, with the same abundance of galaxies, the same clustering properties, the same distribution of masses and sizes, and the same large-scale structure. If the ring appears in the simulations with roughly the same frequency and properties as in the observations, then the ring is explained. It is a natural outcome of the standard processes realized in one particular region of space that happens to be observable from our location. If the ring does not appear in the simulations or appears much less frequently than observed, then the explanation is incomplete. Possible reasons for a discrepancy include missing physics, such as the effects of magnetic fields, cosmic rays, or turbulence, which are often treated in simplified ways or omitted entirely from simulations because of computational expense. Another possibility is that the initial conditions are not perfectly characterized, and there are features in the primordial power spectrum or the distribution of primordial perturbations that are not captured by current measurements of the cosmic microwave background. A third possibility is that the observations themselves are subject to systematic errors or biases that make the ring appear more significant than it actually is. Distinguishing these possibilities requires a painstaking comparison of models and data. varying assumptions, testing different scenarios, and seeking independent confirmation through complementary observations. Independent confirmation means observing the ring with different telescopes, different instruments, and different techniques. Webb provides the most sensitive infrared observations, but other observatories can contribute. Ground-based telescopes equipped with wide-field cameras and spectrographs can survey the ring region to greater depth and over larger areas, providing more redshifts and more complete sampling of the galaxy population. Radio telescopes can detect the neutral hydrogen gas in the galaxies, tracing the fuel available for star formation and the dynamics of the gas. X-ray telescopes can detect the hot gas in clusters within the ring, if such clusters exist, and measure their temperatures and densities, which constrain the masses and formation histories of the clusters. Gravitational wave detectors, while not directly observing the ring, can provide information about the merger history of compact objects, like black holes and neutron stars in the ring's member galaxies, offering a different perspective on the rate of star formation and galaxy evolution. Each of these observations adds a layer of understanding, and the combination of multi-wavelength, multi-messenger data provides a much richer picture than any single dataset alone. Multi-messenger astronomy is a relatively new term, referring to the use of multiple types of signals, photons at different wavelengths, neutrinos, and gravitational waves, to study the same sources. For large-scale structures like the ring, the primary messengers are photons, but the principle of combining different types of information still applies. Photometric observations provide positions and brightnesses. Spectroscopic observations provide redshifts and physical properties. Lensing observations provide mass distributions. Radio observations provide gas content. Each type of observation is sensitive to different aspects of the structure, and each is subject to different systematic uncertainties. Combining them reduces the overall uncertainty and provides consistency checks that increase confidence in the results. If the different observations all point to the same conclusion, that the ring is a real structure with certain properties, the conclusion is robust. If the observations disagree, it indicates that at least one of them is affected by systematics that need to be understood and corrected. Systematics are the bane of precision measurements. Unlike statistical uncertainties, which decrease with more data, systematic uncertainties can remain constant or even grow if the underlying issue is not addressed. Common sources of systematics in astronomical observations include calibration errors, where the measured brightness or wavelength of a source does not accurately reflect the true brightness or wavelength. Foreground contamination, where light from intervening objects or the telescope itself is mistaken for light from the target. And selection effects, where the sample of objects studied is not representative of the population as a whole because of the way the sample was chosen. In the case of the ring, possible systematics include errors in the redshift measurements, which would affect the inferred distances and the three-dimensional structure. Photometric calibration errors, which would affect the measured brightnesses and therefore the inferred masses and star formation rates, and selection biases, where the criteria used to select galaxies for study preferentially include or exclude certain types of galaxies in ways that could enhance or suppress the appearance of the ring. Addressing systematics requires careful validation of the data reduction and analysis procedures. This includes comparing different methods for measuring redshifts and checking that they give consistent results. cross-checking photometric calibrations against standard stars or other objects with well-known brightnesses, and testing the sensitivity of the results to variations in the selection criteria. It also includes blind tests, in which the analysis is performed without knowledge of the expected outcome, to avoid confirmation bias, and the use of simulated data, where the true properties are known, to check that the analysis recovers those properties accurately. These steps are standard practice in modern observational astronomy, but they are time-consuming and require significant effort. The fact that the ring has been reported in the literature indicates that the initial analyses have passed these checks, but continued scrutiny as more data become available is essential to ensure that the detection is not an artifact. Artifacts in astronomical data have a long history. Apparent structures that turned out to be instrumental effects, calibration errors, or misinterpretations of noise have appeared repeatedly in the history of the field. The canals of Mars, thought to be evidence of intelligent life, were artifacts of the human eye's tendency to connect disconnected features and the limitations of telescopes at the time. The claimed detection of a planet orbiting a pulsar, announced in the early 1990s, was initially heralded as the first exoplanet discovery, but was later retracted when it was found to be an error in the analysis. The detection of superluminal motion in quasars was initially puzzling, but was eventually understood as a projection effect combined with relativistic motion, not a violation of the speed of light. Each of these examples underscores the importance of skepticism and rigorous verification in interpreting observations, especially when the observations suggest something unusual or unexpected. The ring is unusual, and its detection warrants skepticism. But skepticism is not the same as dismissal. The data supporting the ring's existence come from one of the most advanced and carefully calibrated instruments ever built, and the analysis has been performed by experienced researchers using state-of-the-art techniques. The structure has been detected independently in multiple datasets and using multiple methods, which strengthens the case for its reality. The next phase involves deeper observations, expanded analysis, and comparison to simulations, all aimed at refining our understanding of what the ring is and what it means. This process is ongoing, and it is too early to draw definitive conclusions. What can be said is that the ring is a feature of the galaxy distribution at moderate redshifts that exhibits a coherent geometry suggesting a large-scale structure, and that this structure is not obviously predicted by existing models, but is not yet inconsistent with them. Consistency with models is a moving target. As models improve, they make more precise predictions, and structures that were once considered rare or anomalous may become expected. Conversely, as observations improve, structures that were once thought to be consistent with models may turn out to be in tension with them when the details are examined more closely. The ring is currently in a state of tension, meaning it is at the edge of what the models comfortably predict, but not yet beyond that edge. Whether it remains in this state or moves into or out of tension depends on future observations and future simulations. The outcome will have implications not just for our understanding of this particular structure, but for our understanding of structure formation in general, the nature of dark matter, the properties of dark energy, and the validity of the cosmological principle on the largest scales. Dark energy, the mysterious component driving the accelerated expansion of the universe, affects structure formation by opposing the gravitational pull that draws matter together. As the universe expands, the density of matter decreases, but the density of dark energy, if it is a cosmological constant, as the simplest models assume, remains constant. Eventually, dark energy dominates and the expansion accelerates, making it harder for structures to grow. The transition from matter domination to dark energy domination occurred relatively recently in cosmic history at a redshift of around zero point 0.5 to 1, roughly the epoch at which the ring is observed. This timing might be relevant. If the ring is a structure that was in the process of forming when dark energy began to dominate, its growth might have been stunted, leaving it in a state intermediate between a collapsing structure and a relaxed one. Alternatively, the ring might represent a structure that formed earlier when matter domination was still strong and is now evolving slowly under the influence of dark energy. Distinguishing these scenarios requires detailed modeling of the ring's dynamics and comparison to the predictions of models with and without dark energy. Models without dark energy, while disfavored by a wide range of observations including supernova distances, the cosmic microwave background, and the growth of structure, are still explored as alternatives or as tests of the robustness of the standard model. In some of these models, the accelerated expansion is explained by modifications to general relativity rather than by a new component of the universe. And the growth of structure can differ in subtle ways from the standard predictions. If the ring's properties are found to be inconsistent with lambda CDM, but consistent with a modified gravity model, it would provide a new line of evidence relevant to the dark energy debate. However, such a conclusion would require not just consistency with one alternative model, but inconsistency with the standard model at a level that cannot be explained by uncertainties or systematics. A very high bar to meet. The bar is high because the standard model is so successful. It explains the expansion history of the universe from the first few minutes after the Big Bang to the present, the formation of light elements in Big Bang nucleosynthesis, the spectrum and anisotropies of the cosmic microwave background, the formation and evolution of galaxies and clusters, and the distribution of large-scale structure. It does so with a small number of parameters, all of which have been measured with increasing precision over the past few decades. The parameters include the densities of matter, and dark energy, the expansion rate of the universe, the amplitude and tilt of the primordial power spectrum, and a few others related to the properties of neutrinos and the reionization of the universe. These parameters are constrained by combining data from multiple independent observations, and the fact that the constraints from different observations agree with one another is a powerful validation of the model. For a single observation, like the ring, to challenge this edifice, it must be not just unusual but incompatible in a way that cannot be accommodated by adjusting the parameters within their allowed ranges, or by invoking plausible but currently uncertain physics. Uncertain physics abounds in astrophysics. Galaxy formation is governed by processes that span an enormous range of scales, from the quantum mechanics of atomic cooling to the gravitational dynamics of dark matter, halos spanning millions of light years. Bridging these scales requires simplifications and approximations, parameterizations of processes that cannot be modeled from first principles, and tuning of parameters to match observations. Star formation, feedback from supernovae and active galactic nuclei, the accretion of gas onto galaxies, the stripping of gas in dense environments, and the mergers of galaxies are all processes that affect the distribution and properties of galaxies, and are all subject to significant uncertainties. These uncertainties propagate into predictions of large-scale structure, meaning that even if the dark matter distribution is predicted accurately by simulations, the distribution of galaxies can differ depending on how these processes are treated. The ring's properties might fall within the range of uncertainty associated with these processes, in which case it would not challenge the standard model, but would simply reflect the complexity of galaxy formation. Complexity is both a challenge and an opportunity. It is a challenge because it makes predictions more difficult and increases the number of parameters that need to be constrained. It is an opportunity because it means that observations like the ring can be used to learn about the processes themselves. By comparing the observed properties of galaxies in different environments to the predictions of models with different assumptions about star formation, feedback, and gas physics. The ring provides a unique environment, a large-scale overdensity at a particular epoch, and comparing the galaxies within the ring to those in the surrounding field or in clusters at the same redshift can reveal how environment influences galaxy evolution. This kind of comparative study is a staple of extragalactic astronomy and has been used to understand the role of environment in quenching star formation, transforming galaxy morphologies, and regulating the growth of supermassive black holes. Supermassive black holes sit at the centers of most galaxies, including the Milky Way, and their growth is intimately tied to the growth of the galaxies themselves. The relationship between black hole mass and the mass or velocity dispersion of the host galaxy's bulge is one of the tightest correlations in astrophysics, suggesting that black holes and galaxies co-evolve through processes that are not yet fully understood. Feedback from active galactic nuclei, in which energy released by gas falling into the black hole heats or expels the surrounding gas, is thought to play a key role in this coevolution by regulating both the growth of the black hole and the star formation in the galaxy. If the environment of the ring affects the fueling of black holes through enhanced gas inflows due to interactions or mergers, or through reduced gas availability due to heating or stripping, then the fraction and properties of active galactic nuclei in the ring should differ from those in other environments. Measuring these differences requires spectroscopy to identify active galactic nuclei through their characteristic emission lines, and to measure their luminosities, which trace the accretion rates onto the black holes. Accretion rates are difficult to measure directly because we observe the radiation emitted by the accretion process, not the accretion itself. The relationship between the observed luminosity and the accretion rate depends on the efficiency with which the gravitational potential energy of the infalling gas is converted into radiation, a quantity that depends on the black hole's spin, the structure of the accretion disk, and the presence of jets or winds. Typical efficiencies are around 10%, meaning that 10% of the rest mass energy of the accreted gas is radiated away, but the actual value can vary. Despite these uncertainties, luminosity is a useful proxy for accretion rate, and comparing the distribution of luminosities for active galactic nuclei in different environments provides insight into how environment affects black hole growth. If the ring shows an excess of luminous active galactic nuclei, it might indicate that the environment is conducive to major mergers or gas-rich interactions that funnel gas toward the black holes. If it shows a deficit, it might indicate that the gas has been depleted or heated, reducing the fuel available for accretion. Gas depletion and heating are consequences of both internal processes, such as feedback from star formation and active galactic nuclei, and external processes, such as ram pressure stripping in dense environments or strangulation, in which the galaxy is deprived of fresh gas from the intergalactic medium. The relative importance of these processes varies with environment, with ram pressure stripping being most important in clusters, where galaxies move at high speeds through a hot intracluster medium, and strangulation being important in smaller groups or filaments, where the density is lower, but the gas can still be heated or expelled by various mechanisms. The ring, being a large-scale structure but not a virialized cluster, represents an environment intermediate between the field and clusters, and studying the gas content of its member galaxies can reveal which processes are active. Gas content can be traced through observations of molecular gas, which emits at millimeter and radio wavelengths and is the immediate fuel for star formation, and atomic gas, which emits at 21 centimeter wavelength and represents the reservoir from which molecular gas forms. 21 centimeter emission from neutral hydrogen is a powerful probe of the gas content and kinematics of galaxies. The emission line is narrow and uncontaminated by other lines, making it possible to measure redshifts and velocities with high precision. Large radio surveys, such as those conducted with the Very Large Array and the future Square Kilometer Array, can map the distribution of neutral hydrogen in and around galaxies, revealing tidal tails from interactions, gas streams feeding galaxies, and the effects of ram pressure stripping. If the galaxies in the ring have been affected by their environment, their neutral hydrogen distributions should show signatures of these processes. Combining radio observations with the infrared observations from Webb provides a comprehensive picture of the interplay between gas, stars, and environment, and helps to answer the question of whether the ring environment is fundamentally different from other environments at the same epoch. Epoch matters. The universe evolves, and the properties of galaxies and large-scale structures at one epoch are not the same as at another. At higher redshifts, corresponding to earlier times, the universe is denser, galaxies are smaller and more irregular, star formation rates are higher, and the cosmic web is still assembling. At lower redshifts, corresponding to more recent times, the universe is more diffuse, galaxies are larger and more regular, star formation rates are lower, and the cosmic web is more mature. The ring, observed at a redshift of around 0.2 to 0.5, corresponds to an era roughly 2 to 5 billion years ago, when the universe was already quite mature, but still more active than today. Comparing the properties of the ring and its galaxies to those of structures and galaxies at higher and lower redshifts allows us to place the ring in an evolutionary context, understanding it not as a static entity, but as a snapshot of a system in the process of changing. Change is the fundamental fact of cosmic history. The universe began in a hot, dense state and has been expanding and cooling ever since. Matter condensed out of the primordial plasma, forming atoms, molecules, stars, and galaxies. Stars produced heavy elements, which enriched the gas and changed the conditions for subsequent generations of stars. Galaxies merged and interacted, building larger galaxies and altering the star formation histories of the participants. Dark energy began to dominate, slowing the growth of structure and accelerating the expansion. Each of these changes left an imprint on the universe we observe, and by reconstructing the history, we can test our understanding of the fundamental physics governing cosmic evolution. The ring is a piece of this history, a structure formed at a particular time under particular conditions, and its study contributes to the broader effort to understand how the universe came to be as it is. Reconstruction of cosmic history relies on observations at many redshifts, building up a timeline from the earliest moments, probed by the cosmic microwave background and the most distant galaxies, to the present day, probed by nearby galaxies and the local large-scale structure. Each observation provides a snapshot, and the snapshots are assembled into a movie, a dynamic picture of the evolving universe. The frames of this movie are not evenly spaced. The cosmic microwave background provides a single, highly detailed frame at a redshift of around 1000. The epoch of ionization, when the first stars and galaxies ionized the neutral hydrogen filling the universe, is captured in observations of high redshift quasars and galaxies at redshifts between 6 and 10. The peak of star formation in the universe, the era when stars were forming most rapidly, occurred at redshifts between 1 and 3 and is sampled by deep surveys with Hubble and Webb. The assembly of massive galaxies and the formation of the modern cosmic web occur at redshifts below 1 and are probed by large area surveys like the Sloan Digital Sky Survey and its successors. The ring, at intermediate redshift, falls into this last category, part of the era when the large-scale structure we see today was taking its final form. Final form is a misnomer. The universe continues to evolve, and the structures we see are not static. Clusters continue to accrete galaxies and merge with other clusters. Filaments continue to channel gas into denser regions. Voids continue to expand as matter flows out of them. Galaxies continue to form stars, though at a declining rate compared to the peak epoch. The Milky Way and Andromeda, the two largest galaxies in the local group, are on a collision course and will merge in roughly 4 billion years, forming a giant elliptical galaxy. The ring, if it persists, will continue to evolve, its member galaxies interacting and merging, its overall structure shaped by the gravitational pull of surrounding matter and the expansion of space. Predicting the future evolution of the ring requires simulations that extend forward in time, tracking the motions of galaxies and the flow of gas under the influence of gravity and dark energy. Such simulations are computationally intensive, but provide insight into the ultimate fate of the structure. Ultimate fate, in cosmology, is often tied to the fate of the universe as a whole. If dark energy is a cosmological constant, the universe will expand forever, with the expansion accelerating without bound. Structures like the ring will become increasingly isolated as space expands between them, and eventually, the expansion will carry galaxies beyond the horizon, out of causal contact. The universe will become cold, dark, and empty, with the last stars burning out trillions of years in the future, and black holes evaporating via Hawking radiation over timescales almost incomprehensibly long. If dark energy is not a constant but a dynamic field that evolves over time, the fate of the universe depends on the properties of that field. Some models predict that dark energy will weaken, allowing structures to resume growth. Other models predict that dark energy will strengthen, leading to a big rip in which the expansion becomes so rapid that it tears apart galaxies, stars, planets, and eventually atoms. Distinguishing these scenarios requires precise measurements of the expansion history and the growth of structure, and observations of structures like the ring contribute to these measurements by providing data on how matter is distributed at different epochs. Epochs are defined by the dominant physical processes. The radiation-dominated epoch, lasting from the Big Bang until a few tens of thousands of years later, was governed by the dynamics of photons and relativistic particles. The matter-dominated epoch, lasting from the end of radiation domination until a few billion years ago, was governed by the gravitational attraction of matter, both dark and ordinary. The dark energy-dominated epoch, which began a few billion years ago and continues today, is governed by the repulsive effect of dark energy on the expansion. The ring formed during the transition between matter domination and dark energy domination, a time when the balance of forces was shifting and the fate of structures was being determined. Understanding the ring means understanding how structures responded to this transition, how their growth was affected by the onset of acceleration, and what the implications are for the future evolution of the universe. Future evolution cannot be observed directly, but it can be predicted with confidence if the underlying physics is understood. The predictions depend on the parameters of the cosmological model, and those parameters are constrained by observations. The more precise the observations, the more tightly the parameters are constrained, and the more confident we can be in the predictions. The ring, as a single structure, does not strongly constrain the cosmological parameters on its own, but it contributes to the overall dataset, and in combination with many other observations, it helps to refine our understanding. Every galaxy, every cluster, every filament, and every void is a data point, and the ensemble of data points allows us to infer the properties of the universe with remarkable precision. Precision in cosmology has increased dramatically over the past few decades. In the early 20th century, the expansion of the universe had just been discovered, and estimates of the expansion rate differed by factors of several. By the late 20th century, the expansion rate was known to within a few tens of percent, and the age of the universe was constrained to be between 10 and 20 billion years. Today, the expansion rate is known to within a few percent. The age of the universe is determined to be 13.8 billion years, with an uncertainty of less than 1%. And the densities of matter, and dark energy are known to within a few percent each. This precision has been achieved through painstaking observations, careful calibration, and the development of ever more sophisticated instruments. Webb is the latest in this lineage, and its observations are pushing the precision even further, allowing us to detect and characterize structures like the ring that would have been invisible to earlier generations of telescopes. Invisible does not mean non-existent. The ring was there all along, its galaxies emitting light that traveled across billions of light years. But that light was too faint, too red, or too diluted among the noise to be detected until Webb provided the sensitivity and resolution needed to pick it out. This is a recurring theme in astronomy: structures and phenomena that exist but remain hidden until the technology advances enough to reveal them. The history of the field is a history of such revelations, from the moons of Jupiter to the rings of Saturn, to the spiral structure of galaxies, to the cosmic microwave background, to gravitational waves. Each revelation expanded our view of the universe and forced us to revise our understanding. The ring is part of this tradition, a feature of the cosmos brought into view by human ingenuity and the relentless push to see farther, deeper, and more clearly. Clarity is the goal of every observation, Raw data are noisy, contaminated by instrumental effects, blurred by the atmosphere or the telescope's optics, and subject to a host of systematic errors. Reducing the data means correcting for these effects, calibrating the measurements, and extracting the signal from the noise. This process is as much an art as a science, requiring experience, intuition, and a deep understanding of the instruments and the physics of the observations. The astronomers who study the ring are experts in this process, and the results they publish represent the culmination of months or years of careful work. But the work is never truly finished. As new data arrive, the analysis is refined, the models are updated, and the understanding deepens. The ring, as we know it today, is a provisional picture, the best that can be done with the data currently available. As more observations are made and as techniques improve, the picture will sharpen, details will emerge, and the true nature of the structure will come into focus. Focus requires not just better data, but better theory. Observations tell us what is, but theory tells us why. The goal of astrophysics is not merely to catalog the contents of the universe, but to understand the principles that govern its behavior. The ring challenges us to apply those principles, to take the known laws of physics and the measured properties of the universe, and to construct a narrative that explains how the ring came to be. This narrative will be tested against observations, refined as new data emerge, and compared to narratives constructed to explain other structures. The process is iterative, with theory and observation informing each other in a feedback loop that drives progress. The ring is one input to this loop, a puzzle piece that must fit into the larger picture of cosmic structure. The larger picture is still incomplete. Despite the tremendous progress of the past century, cosmology remains a field with major open questions. The nature of dark matter is unknown. The nature of dark energy is unknown. The origin of the primordial density fluctuations, while attributed to quantum processes during inflation, is not directly confirmed. The reason for the apparent fine-tuning of the cosmological parameters, such as the coincidence that dark energy began to dominate at roughly the same epoch as when structure formation peaked, is not understood. The formation of the first stars and galaxies, the ionization of the universe, and the assembly history of massive galaxies are all active areas of research with many uncertainties. Each of these questions is being addressed through observations and theory, and structures like the ring contribute by providing new data that constrain the models and by raising new questions that drive further investigation. Investigation is the essence of science. It begins with curiosity, the desire to understand, and proceeds through observation, hypothesis, testing, and revision. The detection of the ring began with observations, the systematic imaging and spectroscopy of a region of sky by Webb. The observations revealed a pattern, an overdensity of galaxies with a particular geometry. The pattern prompted hypotheses. Is this a projection effect, a shell, a filament, a remnant of primordial structure? Each hypothesis makes predictions that can be tested with further observations. The tests are underway, and the results will determine which hypotheses are viable and which must be discarded. This process is slow and painstaking, but it is the only reliable way to arrive at an understanding that is both deep and grounded in evidence. Evidence is the currency of science. Claims must be supported by data, and the data must be reproducible, meaning that other observers using similar methods should be able to confirm the results. The ring has been reported in the scientific literature, which means the data and the analysis have been subjected to peer review, a process in which other experts in the field evaluate the work for soundness and significance before it is published. Peer review is not perfect, and erroneous results sometimes make it through, but it is an essential filter that maintains the quality of the scientific literature. The fact that the ring has passed peer review indicates that the editors and reviewers judged the evidence to be sufficient to warrant publication, but it does not mean the work is beyond question. Other researchers will scrutinize the results, attempt to replicate the analysis, and offer alternative interpretations. This is healthy and expected. Science advances through debate and the confrontation of ideas with evidence. Debate over the ring is likely to be vigorous. Unusual structures attract attention, and astronomers will be eager to test whether the detection holds up under scrutiny and what the implications are for our understanding of the universe. Some will focus on refining the observations, obtaining deeper data, more redshifts, and better three-dimensional mapping. Others will focus on the simulations, running larger or more detailed calculations to see if rings like the observed one appear with sufficient frequency. Still others will explore alternative explanations, considering whether the ring could be an artifact, a projection, or a consequence of physics not included in the standard models. Each of these efforts contributes to the overall assessment, and over time, a consensus will emerge. Either the ring will be confirmed as a genuine and significant structure, or it will be explained away as a combination of less remarkable features, or it will remain ambiguous, awaiting better data to resolve. Resolution takes time. The timeline for resolving scientific questions varies widely depending on the difficulty of the observations, the complexity of the analysis, and the level of interest in the community. Some questions are settled quickly within months or a few years as new data become available and analyses are performed. Others linger for decades, with periodic bursts of progress interspersed with long periods of little change. The ring is likely to fall somewhere in the middle. The observations are difficult but feasible with Webb and other facilities, so data will accumulate over the next several years. The analysis is complex but not intractable, so results will be published as the data are processed. The interpretation is challenging because it touches on fundamental questions about large-scale structure and the cosmological principle, so debate will continue even as more information becomes available. Within 5 to 10 years, we should have a much clearer picture of what the ring is and what it means. What it means depends on the details. If the ring is a rare but allowed fluctuation within the standard cosmological model, it means that the universe is capable of producing larger and more coherent structures than we typically see, and it provides a test case for the statistical properties of the cosmic web. If the ring is inconsistent with the standard model, it means that something is missing or wrong in our understanding, whether in the physics of structure formation, the properties of dark matter, the nature of dark energy, or the initial conditions set by the early universe. Either way, the ring is informative. It tells us something about the universe, and by extension, about the laws of nature that govern its evolution. Laws of nature are the deep principles that underlie all physical phenomena. In cosmology, the relevant laws are general relativity, which describes gravity and the dynamics of spacetime, and the laws of quantum mechanics and thermodynamics, which govern the behavior of matter and energy. These laws are expressed mathematically, and their implications are worked out through calculation and simulation. The fact that these laws, applied to the observed initial conditions and the measured properties of matter and energy, successfully predict the large-scale structure of the universe is a triumph of modern physics. But the laws are only as good as the tests we apply to them, and every new observation is an opportunity to test them again in a new regime. The ring is such a test. If the laws pass, our confidence in them increases. If they fail, we learn something new. Learning is the ultimate goal. Science is not about certainty or final answers. It is about progressively refining our understanding, correcting mistakes, and expanding the domain of knowledge. The ring is a single structure in a vast universe, but it is a structure that has caught our attention because of its geometry and the questions it raises. Studying the ring means asking why it exists, how it formed, and what it tells us about the cosmos. The answers to these questions will be hard-won, the product of years of observation, analysis, and debate. But the effort is worthwhile because every answer opens up new questions, and the pursuit of those questions drives the field forward. Forward motion in cosmology is relentless. Each generation of astronomers builds on the work of the previous generation, using better instruments, more sophisticated techniques, and deeper theoretical insights. The questions change as the knowledge base expands, but the fundamental drive to understand remains constant. The ring, observed in the early operational phase of the James Webb Space Telescope, is part of this ongoing endeavor. It is one discovery among many that Webb will make, one structure among countless others in the universe. But it is a structure that has captured attention and that will be studied intensively in the years to come. The results of that study will contribute to our understanding of the cosmos, and they will shape the questions that the next generation of astronomers will pursue with the next generation of instruments. Instruments are the tools of discovery, and their capabilities determine what can be learned. Webb represents a leap forward in infrared astronomy, with sensitivity and resolution far exceeding anything that came before. But Webb is not the final word. Plans are already underway for even more powerful telescopes, both in space and on the ground, that will probe the universe in new ways and at new wavelengths. The extremely large telescope, with a primary mirror 40 meters in diameter, will provide unprecedented resolution in the optical and infrared. The Square Kilometer Array, a network of radio telescopes spread across continents, will map the radio sky in exquisite detail. The Roman Space Telescope, with a field of view much larger than Webb's, will conduct massive surveys of the sky, detecting billions of galaxies and tracing the large-scale structure with unprecedented completeness. Each of these facilities will contribute to the study of structures like the ring, providing complementary data that will enrich our understanding and test our models in new ways. Models evolve as data improve. The standard cosmological model, Lambda CDM, has been refined continuously since its inception, with parameters adjusted as measurements become more precise, and new physics incorporated as it becomes relevant. The model is not static, and it is not dogma. It is a working hypothesis, the best explanation currently available for the observations, subject to revision if new data require it. The ring, depending on how its properties are ultimately assessed, could lead to refinements in the model, adjustments to the parameters, or the incorporation of additional physics. Or it could simply be accommodated within the existing framework, a rare but allowed structure that reinforces the model's validity. Only time and continued observation will tell. Time in cosmology is measured in billions of years, but the time required to answer specific questions can be much shorter. The ring was detected within the first few years of Webb's operation, and the basic properties of the structure should be well characterized within the next 5 to 10 years. Detailed follow-up, including lensing studies, gas observations, and comprehensive spectroscopy, will take longer, perhaps a decade or more, depending on the availability of telescope time and the pace at which data are acquired and analyzed. But the timeline is not solely determined by technology. It is also determined by the priorities of the scientific community, the availability of funding, and the decisions made by the agencies and organizations that operate the telescopes. These factors are all subject to change, influenced by discoveries, by shifting interests, and by the broader context in which astronomy is practiced. Context includes not just the scientific questions, but also the human endeavor of science itself. Astronomy is practiced by people, and those people bring their own perspectives, biases, and motivations to the work. The study of the ring involves teams of researchers, each contributing expertise in observation, instrumentation, data analysis, or theory. Collaboration is essential because no single person has all the skills required to tackle the complex questions raised by structures like the ring. The teams communicate through papers, conferences, and informal discussions, sharing results, debating interpretations, and building on each other's work. This collaborative process is one of the strengths of science, allowing progress to be made more rapidly and reliably than any individual could achieve alone. Alone, no structure in the universe can tell us everything. But together, the ensemble of observations from the cosmic microwave background to the large-scale distribution of galaxies to structures like the ring forms a coherent picture of the universe's history and evolution. Each observation constrains the models in a different way, and the constraints are combined to arrive at the best overall fit to the data. The ring is one piece of this ensemble, contributing its own unique information and raising its own questions. As the dataset grows and the models improve, the picture will become sharper, the uncertainties will shrink, and our understanding will deepen. Understanding the universe means understanding how it came to be, how it has evolved, and how it will change in the future. It means tracing the chain of causation from the initial conditions set by the Big Bang and inflation to the formation of the first atoms, the first stars, the first galaxies, and the first large-scale structures. It means understanding the roles played by dark matter, dark energy, ordinary matter, and radiation in shaping the cosmos. It means grappling with the fact that most of the universe is invisible, detectable only through its gravitational effects, and that the visible universe is just a small fraction of the whole. It means confronting the possibility that our universe is one among many, part of a multiverse in which the parameters we measure are not fundamental constants, but accidents of our particular cosmic environment. These are grand questions, perhaps the grandest that science can address, and they are pursued through the patient accumulation of evidence, one observation at a time. One observation at a time, the universe reveals itself. The ring is one revelation, a pattern in the distribution of galaxies that was hidden until the technology existed to detect it. Its discovery does not answer all the questions about large-scale structure, but it adds to the body of knowledge, providing a new constraint, a new puzzle, and a new opportunity to test our understanding. The process is slow and the answers are often incomplete or provisional, but this is the nature of science. Progress is incremental, built on the work of countless individuals over generations, each contributing a small piece to the larger whole. The larger whole is the universe itself, vast beyond comprehension, filled with structures and phenomena that challenge our intellect and inspire our curiosity. The ring of galaxies surrounding the Milky Way, detected by the James Webb Space Telescope, is one such phenomenon. It is a structure hundreds of millions of light years across, composed of galaxies that formed billions of years ago, arranged in a geometry that suggests order and coherence in a universe often perceived as chaotic. Its existence prompts questions about how such structures form, why they appear as they do, and what they reveal about the fundamental processes that shape the cosmos. The answers to these questions are being pursued through observation, simulation, and theory, and they will emerge gradually as the data accumulate and the models are refined. Refinement is an ongoing process, never truly complete. Every measurement has uncertainty, every model has assumptions, and every interpretation is subject to revision. The ring, as we understand it today, is a snapshot, a preliminary assessment based on the data available. As more observations are made, the picture will change, details will be added, and some aspects may be reinterpreted or corrected. This is not a weakness of the scientific method, but a strength. Science is self-correcting, constantly updating its conclusions in light of new evidence. The ring will be studied for years, perhaps decades, and our understanding of it will evolve as the investigation continues. Evolution of understanding is the essence of scientific progress. What we know about the universe today is vastly more than what was known a century ago, and what will be known a century hence will surpass what we know now. The ring is part of this trajectory, a discovery made possible by the current generation of technology and the accumulated knowledge of past generations. Its study will inform future discoveries and will contribute to the questions that future astronomers will pursue. The chain of knowledge extends forward and backward, linking past, present, and future in a continuous effort to comprehend the cosmos. Comprehension is perhaps too strong a word. The universe is larger, older, and more complex than any human mind can fully grasp. But we can understand pieces of it, patterns and principles that apply across vast scales and epochs. And we can use that understanding to make predictions, to explain observations, and to push the boundaries of the known. The ring of galaxies surrounding the Milky Way is one of those pieces, a structure that has been brought into view by the most advanced telescope humanity has ever built. It is a reminder of how much remains to be discovered, how much lies beyond the reach of current instruments, and how much we have yet to learn. The study of the ring is not just about the ring itself, but about the broader effort to understand the universe, to trace its history, and to uncover the laws that govern its evolution. The universe does not care whether we understand it. It exists, evolves, and will continue long after humanity is gone. But we are part of the universe, products of its evolution, and our capacity to observe and understand is one of the ways the universe has come to know itself. The ring of galaxies, a vast structure of light and matter stretching across the void, is both a subject of study and a symbol of the reach of human curiosity. It stands at the intersection of observation and interpretation, a feature of the cosmos that we can detect, measure, and analyze. But that also challenges us to explain and to understand. The effort to meet that challenge is ongoing, and the results will be part of the legacy that this generation of astronomers leaves to the next.